Okay, so the probability generating function for the Poisson distribution. So x Poisson lambda, and you may not remember this because we don't use this formula that much really, but in Poisson the probability x equals x is e to the minus lambda, lambda to the x over x factorial. If you go back to Poisson, we did talk about that at the time, but yeah. I'll leave that there for now. The other thing you'll need for the proof that I'm going to do in a minute, or it's not quite a proof, but we're showing a result, is the series expansion for e to the power x. We're going to do quite a lot of work on series, so we'll look at this and some other series at this point, but for any real number x, e to the power x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and that's an infinite series. So you may or may not have seen that before, but we will be looking at those next term sometime. So, example. So we've got a discrete random variable x, which is Poisson, lambda is 1.1. And we want to show from first principles the probability generating function of x is given by the following. I'm going to set this out in a table actually. If you look at this in your book, they've, I believe, used sigma notation a bit more for this. So either or's fine, but I think it's possibly a bit easier to see in a table. So like we did with the binomial, so we've got x and the probability that x equals x. Poisson, like binomial, starts at 0 because you could have no events occurring within a given stretch of space or time. And then going up in ones, the difference mainly in here is that Poisson is an infinite distribution. And then for this one, lambda is 1.1, so the probability x equals x is equal to e to the minus lambda, lambda to the x over x factorial. So that's what we're using. So the probability x equals 0, 1.1 to the 0 and 0 factorial both equal 1. So that will give you e to the negative 1.1. The probability that x is equal to 1, I'm going to pop the 1.1 in front of the e, so it'd be 1.1 e to the negative 1.1 all over 1 factorial, which is just 1. The probability x is 2, so I'm substituting 2 into here and here, is 1.1 squared. I don't really need a bracket on that, it might make it look a little bit clearer. And that's all over 2 factorial, and then 1.1 cubed e to the negative 1.1 over 3 factorial, etc. I think that's enough for you to see what's happening. And so creating the probability generating function g xt for this Poisson distribution. So I need to add a t in here, a t squared here, t cubed here, etc. And I need to, well, I don't need to, but I'm going to pull out this e to the negative 1.1, which is running right through. So it's e to the negative 1.1, and then 1 plus 1.1t plus 1.1 squared over 2 factorial t squared plus 1.1 cubed over 3 factorial t cubed. So you can quite clearly see those t's acting as place values through. And then if I just rewrite that very slightly differently, so that I'm going to pull the 1.1 and the t into the same power. So that's like having 1.1t squared over 2 factorial plus 1.1t cubed over 3 factorial plus, sorry, I forgot my plus, it's an infinite distribution, so it will keep going. So that pattern's sort of quite clear there. And then if we look at what's happening with e to the x, so 1 plus x squared over 2 factorial, x cubed over 3 factorial. So if I replace x with 1.1t in there, we will get this. I think that should be quite clear. So this is equal to e to the negative 1.1 times e to the 1.1t. If we multiply, then we add the powers. Which takes us to there, and then if you pull 1.1 out as a factor, we get e to the 1.1 lots of t minus 1 as a probability generating function of x, which, you know, if you don't know that series expansion for e, looks a bit odd, but as soon as you know the series expansion for e, it kind of makes sense. That can be generalised, which I'll pop on the other board. So if x is Poisson lambda, then the probability, notation, the probability generating function for x, which we write like this, is equal to e to the power lambda lots of t minus 1. Again, that's in the formula book. And that obviously matches what we've done there. So that's a result that you can use, but if you need to show from first principles that you get this result, then you need to go through a process like this. If you'd rather use sigma notation, have a look at the example in the book, but I just think it's a little bit easier to see that way in some respects.